Hi guys, this is the Electric Tutor. I'm going to talk about arc length today. And before we go into our two examples, I want to show you where the equation for it comes from because it's simple and I know it's going to help you guys understand the topic a little bit better and remember the formula. So let's go for it. In calculus, you already know that we're interested in, we typically have a function, f of x or whatever, and our interest is to be able to calculate, or one of our biggest interests is to calculate the area underneath that function from any given interval of interest from a to b. But have you ever asked yourself, can I know just the length of that, of the line itself, of the function that we're working with? And if that is of your interest, then this is the video for you, because we can actually do this. And as you know, with straight lines, traditionally we just look at the distance formula. However, in this case, we don't have a straight line. But if we apply our calculus mindset and we zoom into that line as many times as possible, in fact, if we zoom, let's say, quote unquote, infinitely many times to whatever interval, then we would basically have some straight line. And if I put some coordinates here, it would be, let's say, x1, y1, and then in here we would have x2, y2, something like that. Now we have a straight line, right? And if we draw a little right triangle here, we would know that this length is the hypotenuse. So the distance of the hypotenuse, since this is a straight line, would basically be the distance formula. So the square root of delta x, which is like x2 minus x1 squared, plus y2 minus y1 squared, and we would get it. Now, if we calculate, if we were to calculate many of these, and then add all those small distances up, then we would obtain the exact arc length of this function, again from a to b. Okay, so this is where this little derivation comes from. So the distance of a function, of an arc or line that is not straight, or basically in general terms, is going to be the square root of, again, delta x plus delta x squared plus delta y squared. In this case, this would be x2, x sub 1, so on and so forth. And then what we're doing here is we're adding up n many small intervals to make, to just compensate for the entire actual length, assuming that these lines or segments are very small. And we haven't applied that yet mathematically. We're just adding up all of those segments. Here we're just rewriting it, delta x and delta y. It's easier. Now we want to rewrite this as something like an integral, right? Because we're in Calc 2. So we're obviously going to apply a limit eventually, but we need a differential on the outside. So what I'm going to do is I'm going to try to take this delta x to the outside, and this is how I do it. It's not hard. We multiply the delta y by 1. In this case, delta x squared over delta x squared. What this does is we can then factor out these delta x's, right? And then we're left off with this. And then this cancels out. We can move that to the outside. And then now that we have our delta x on the outside, we can apply the limit as n goes to infinity, implying, the segments are infinitely small. And we have our equation here. This, of course, simplifies to just integral notation from a to b of 1 plus delta y over delta x is basically f prime, so f prime squared. We can simplify it even more, and this would be our formula. We're going to use this for every single arc length exercise in a Calc 2 course, okay? So let's look at our first example. So we wish to know the length of this function, and it goes from 1/2 to 2. This is A, this is B. And we follow up our formula. The first thing I always like to do is to find f prime. So that would be my step 1. So fx is x cubed over 6 plus 1 over 2x. F prime is then going to be x squared over 2 minus 1 over 2x squared. And I see two 2's in the denominator, so I'm going to factor that out just in case I need it later. And I get this. The second step I like to do is square up that f prime. I just like to do it in separate steps to make it as simple as possible, even though I always write a little bit more, I guess, than necessary. But I'm almost guaranteed that I'm not going to make any mistakes whatsoever. I want to square this last result. So 1/2 squared is 1/4. And then if we square what's inside, it's x squared squared is x to the 4th. Minus 2 times x squared over x squared, that's 2. Plus 1 over x squared squared is 1 over x to the 4th. So basically, which would be my last step, is to put that f prime squared inside our arc length equation. So the length is going to be the integral from a, which is 1/2, to b, which is 2, of square root, and then just substitute that in. So 1 plus 1/4 x to the 4th minus 2 plus 1 over x to the 4th dx. I want to clean this up a little bit, so I'm going to distribute the 1/4 and then add that 1. And this is what we get. We get 1/2 plus 1/4 x to the 4th plus 1/4 1 over 4 x to the 4th, basically dx. I want to make a small note here. To note that x squared plus 1 over x squared when we do that, we get x to the 4th plus 2 plus 1 over x to the 4th, which is literally the same thing over here if we factor out a 1/4. Okay, so this would be 1/4, or I'm just going to rewrite it as 1/2 squared times x squared plus 1 over x squared squared. The reason why I do that is because this is going to cancel with the square root as well as this one. So I'll be left off the integral from 1/2 to 2, and I have a 1/2, and I'm going to write that here on the outside. Integral of x squared plus 1 over x squared dx, which is x to the 3rd over 3 minus 1 over x. This all times 1/2. Evaluate it from 1/2 to 2, which gives you 33 over 16, or approximately 2.1. That would be your result. Here's another example. It's basically the same question, now with a different function, and since it goes from x equals 0 to x equals pi over 4. So obviously this is going to be A, this is going to be B. First step, we want f prime. So if f of x is natural log of cosine x, then f prime is derivative of natural log is 1 over the argument times, because of the chain rule, the derivative of the argument, which is minus sine x, which simplifies to minus tangent x. If we square that, I don't even have to write this, but for the sake of being consistent, I have tangent squared of x. So the length is the integral from a, which is 0, to pi over 4 of root 1 plus tangent squared. Notice that this is the same as secant squared, which is awesome because the square and the root cancel. We basically just have integral of secant x, which is a basic integral. If you can remember what it is, then you will solve it. So it's natural log of absolute value secant x plus tangent x. Now we're basically done. We just have to substitute, obviously, but in case you're not allowed to use a calculator, I'm just gonna show you how I would do it, like step by step. So natural log secant pi over 4 tangent pi over 4 minus natural log secant 0 plus tangent 0. So how do I do this? Well, I don't know by memory like what the secant of pi over 4 is. I don't even know what tangent pi over 4 is, to be honest. So what I do is, I know that secant is 1 over cosine, and I know what cosine of pi over 4 is. That's easy. It's square root of 2 over 2, which is the same thing as 1 over root 2. This is very important. You should know that. So this is very convenient because if we take the reciprocal, we just get root 2. And that's basically the secant of pi over 4. Now, tangent is sine, obviously sine over cosine. Sine of pi over 4 and cosine of pi over 4 are the same. So it basically simplifies to a 1. And now for secant 0, cosine of 0 is 1, 1 over 1 is 1. And in here we know that sine of 0 is 0, so this goes 0. So this is just natural log square root 2 plus 1, and I can get rid of the absolute value bars because this is a positive number, minus the natural log of 1, which is 0. So this would be your result, and if you have access to calculator, it should give you 0.88.